Hello and welcome to the AI Research Roundup. I'm your host Alex, and on this podcast we dive into some of the latest developments in AI research. Today we're looking at a paper called SageAttention2, Efficient Attention with Thorough Outlier Smoothing and Per-Thread INT4 Quantization. Essentially, the researchers are building on previous work to make the attention mechanism in AI models even faster. They propose using really low precision formats, like 4-bit integers for some calculations, and 8-bit floating point for others, along with some new techniques to maintain accuracy. The goal is a big speed up without hurting model performance too much. Okay, so figure 1 here really highlights the performance benefits they achieved. On the top left, you can see a bar chart comparing the kernel speed on an RTX 4090 GPU, SageAttention2, that's the green bar, reaches 481 HEOPS, which is about 3 times faster than FlashAttention2 shown in red. Then next to that, they show the end-to-end speedup for a specific task. It's 1.7 times faster. And those heat maps beside it suggest that the accuracy remains pretty high, very comparable to the baseline. And finally, the video examples at the bottom. Well, they show SageAttention2 generating video frames almost twice as fast, 1.8 times faster, without any noticeable drop in the visual quality compared to the original method. So it's faster in practice, not just in theory. Okay, so building on those performance results we just saw, figure 2 here gives us a look under the hood at the actual workflow of SageAttention2. It shows the 5 main steps. First, they smooth the Q and K matrices, and optionally V, by subtracting the mean. Then, step 3 is where the quantization happens. Q and K go down to INT4 using this per-thread method, while V is quantized to FP8 per channel. Step 4 is running the main kernel, and finally step 5 involves adding back a correction term derived from those means they subtracted earlier. It's this process that allows them to use those lower precision formats effectively. Right, so we saw that workflow uses INT4 and FP8. This table 1, gives us some context on why that FP8 part is beneficial. It compares the speedup you get from different matrix multiplication settings compared to a standard FP16 baseline calculation. You can see that, well, on GPUs like the RTX 4090 and the H100, using FP8 inputs for the matrix multiply gives a 2x speedup over using FP16. This hardware-level speedup is part of what SageAttention2 leverages, especially for that PV calculation step we saw in the workflow. We just saw why using formats like FP8 is beneficial for speed. Now, figure 3 gives us a visual idea of what the actual data looks like inside those Q, K, and V tensors before quantization. It shows heat maps, basically color-coded maps of the values, for 2 different models, Llama 3.1 on the left and CogVideoX on the right. What you can see, especially in the Q and K tensors, are these vertical stripes. Those indicate channels with significantly different value ranges, or outliers. These outliers are exactly what makes low-bit quantization tricky, and it motivates the smoothing techniques we saw in the workflow diagram earlier. Okay, so we saw those outlier stripes in figure 3 that make quantization difficult, especially for Q and K. This figure here gives us a more detailed look at one of the main techniques they use to tackle that. It's called per-thread quantization. Basically, instead of using one scale for a whole block of data, or one for every single token, which can be slow, they group tokens based on the GPU thread that's processing them within a hardware unit called a warp. You can see on the left how different tokens get associated with these quantization scales, the delta Q and delta K values. And then the middle and right parts show how this maps nicely onto the GPU's matrix multiplication hardware. Each thread, like T0, T1, T2, handles calculations using just one specific scale. This helps manage those value variations we saw earlier more effectively during the INT4 quantization step. So we just talked about how they handle Q and K with that per-thread quantization. This table, table 3, it actually spells out the specific quantization details for the 2 main kernel implementations of SageAttention2 that they developed. You can see there are 2 versions listed, SageAttention2 4B, and SageAttention2 8B. The main difference is how they quantize Q and K. The 4B kernel uses INT4 per thread, while the 8B kernel uses INT8 per thread. But importantly, both versions use FP8 for the P and V parts of the calculation. This gives them a couple of options to balance speed and accuracy. Okay, so we just saw the specific quantization setups for the 4B and 8B SageAttention2 kernels. Now, let's see. Table 2 here shows us how those kernels actually perform end-to-end on real tasks. It compares SageAttention2, both 4B and 8B versions, against the original full precision models and some other methods across a bunch of different benchmarks, like Wikitext for language models and clip scores for video models. Looking at the numbers, particularly for the SageAttention2 8B version, the results are really close to the full precision baseline across the board. For example, on Llama 3.1, the Wikitext score is 6.019 for 8B versus 6.013 for full precision. The 4B version shows a tiny bit more difference sometimes, but it's still very competitive. This basically confirms that their techniques achieve those speedups we saw earlier without seriously hurting the final model quality. So yeah, those results really drive home the point. SageAttention2 manages to significantly speed up attention and reduce memory use, especially with that clever per-thread INT4 quantization for Q and K, while keeping performance remarkably close to the original models. This kind of work is super important because it makes these increasingly massive language and vision models actually practical to deploy more widely. Well, that's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm your host, Alex.